Welcome to The Explainer. Today, we're going to completely dismantle everything you might think you know about galaxy collisions. You know, when we hear the word crash, we immediately picture shattered glass, mangled steel, just ultimate destruction. But on a cosmic scale, it's actually the exact opposite. These events are the magnificent billion-year-long engines of cosmic evolution. We're going to see how these immense encounters are actually supreme acts of creation that have literally built the universe as we know it today.
Okay, let's dive right into this by looking at our very own cosmic backyard. We all know the universe is constantly expanding, right? It's driving most galaxies further and further away from one another. But because of immense localized gravitational pulls, massive collisions still happen. In fact, right now, our Milky Way and our giant neighbor, the Andromeda Galaxy, are being inexorably drawn together. It is a high-stakes, slow-motion impending impact. So, what exactly goes down when two colossal titans like this finally meet?
Well, to understand the sheer scale of this, we really have to wrap our heads around the staggering timescales involved. Right now, we're in the approach phase, driven by what astrophysicists call peculiar velocity. Basically, it's a localized gravitational attraction that's strong enough to just overpower the expansion of the universe. In about 4.5 billion years, the first physical intersection is going to happen when their massive dark matter halos actually touch. Over the hundreds of millions of years that follow, the galaxies will go through violent relaxation and intensely massive bursts of star formation. Finally, after a couple of billion years of this crazy cosmic dance, they'll merge entirely, transforming from two beautiful spiral galaxies into one massive elliptical galaxy.
Now, this isn't just some apocalyptic end. It's a spectacular transfiguration. As cosmologist Carlos Frank notes here, this collision is going to completely awaken the dormant, supermassive black hole sitting at our galaxy's core, turning the night sky into this unbelievable display of cosmic fireworks. It's essentially a rebirth. But to really understand how a galaxy gets reborn from a crash, we need to correct a pretty huge misconception about what a galactic collision actually looks like up close.
Section 2. The empty space paradox. And this brilliantly illustrates what we mean by that paradox. If you picture stars violently smashing into each other like cars on a highway, you're definitely not alone. But the physics tells a totally different story. Galaxies are overwhelmingly just empty space. To put this into perspective, if we shrunk our sun down to the size of a ping-pong ball, the nearest star to us, Proxima Centauri, would be the size of a pea, located 1,100 kilometers away. Even in the tightly packed galactic core, you'd basically only have one ping-pong ball every 3 kilometers. Honestly, you'd have better luck winning the lottery than seeing two stars hit head-on. Because the stars are so incredibly tiny compared to the vast distances between them, the chance of direct star-to-star collisions is statistically zero. The two galaxies will mostly just pass right through each other like ghosts.
So you're probably wondering, if the stars aren't hitting each other, what on Earth is actually crashing? The answer is gravity. These are fundamentally inelastic collisions. Instead of physical stars crashing, the massive gravitational fields of the two galaxies just clash. This invisible friction takes that beautifully ordered merry-go-round orbital motion of the original galaxies and violently rips it into pure chaos. It's this intense gravitational warping, driven by tidal forces, that completely reshapes the architecture of both systems.
Section 3. Gas, shocks, and starbursts.
Now, while the stars might slip past one another like ghosts, the massive clouds of interstellar gas absolutely do not. When this gas collides, it gives rise to something called a starburst. Unlike stars, massive clouds of interstellar gas and dust are highly collisional. When two galaxies interact, tidal torques sweep up a huge fraction of their gas and funnel it right into the central regions. This sudden, severe compression acts like a cosmic pressure cooker, triggering the rapid birth of millions of new stars. So the destruction of the old orbits directly fuels this massive wave of new stellar creation. It's quite literally creation out of destruction.
Take a look at the red points in this simulation of a high-velocity impact, representing a collision happening at a blistering 1,000 kilometers per second. In these incredibly fast hits, shock waves literally strip the warm disk gas straight out of the galaxies. Instead of settling down and forming stars, the gas just splashes out into the intergalactic void, leaving the galaxies totally gas-depleted and fundamentally crippling their ability to form new stars down the road.
Now, what's really interesting about this slide is the massive spike in the star formation rate right here on the data curve. That gigantic spike happens precisely at the moment the two galaxies first touch and their gas reservoirs violently compress. After that initial massive shockwave, the rate absolutely plummets as the gas is dispersed out, before it starts oscillating again as the galaxies swing back around for a second pass. It's essentially a cosmic heartbeat, recorded entirely in the birth of new stars.
Section 4. The invisible forces, dark matter, and black holes.
While all that glowing, superheated gas gives us the visible fireworks, the ultimate fate of the collision is actually decided by the invisible heavyweights in the room. The key mechanic here is dynamical friction, sometimes called Chandrasekhar friction. Because galaxies sit inside these massive, extended halos of dark matter, it's actually those dark matter halos that intersect first. As the dense, star-filled cores of the galaxies plow through this combined dark matter soup, they experience massive gravitational drag. This drag slowly bleeds away their orbital momentum, causing the cores to inevitably spiral inward toward a final, inescapable merger.
And the physics at this scale, they get, honestly, pretty weird. High-velocity collisions can strip gas so violently that it ends up forming entirely new, isolated galaxies that lack any dark matter at all, appropriately named dark matter-deficient galaxies. Just let the gravity of that paradox sink in for a second. We've even observed clusters like Max AJ0025, where dark matter was quite literally separated from regular matter during the crash. And then there are the supermassive black holes. As they spiral toward each other, they act like a giant gravitational slingshot, hurling surrounding stars out into deep space to shed energy, until they eventually run out of ammunition and their orbital decay just stalls out completely.
We actually have a perfect real-world laboratory for these extremes. It's a system nicknamed the Cosmic Owl, which was recently observed by the James Webb Space Telescope way back in the early universe. This one system has everything: twin colliding ring galaxies, dual active supermassive black holes, and this insane bipolar jet blasting right into the collision front, which drives even more shock-induced starbursts. It perfectly shows us how black hole activity and these gigantic galactic crashes work together to rapidly build the early universe.
Section 5. Simulating the wreckage. Since just one galactic collision takes hundreds of millions of years, obviously no human is ever going to live long enough to watch an entire event from start to finish. Instead, astronomers have to piece it all together like a giant puzzle. They look at thousands of different galaxies frozen in different stages of the crash. They use Hubble and James Webb to observe the structural changes, Chandra to track the incredibly hot X-ray gas, and LIGO to literally feel the gravitational ripples of merging black holes. But to really watch a collision unfold dynamically, they use immensely powerful supercomputer codes like Gadget 4 to run n-body and fluid dynamic simulations. This lets them fast-forward millions of years of cosmic history in just a matter of days.
So, the crucial point is that by tweaking the parameters in these simulations, researchers can figure out exactly what drives different outcomes. In the simulation we're looking at here, the galaxies are hitting each other at a blistering 1,000 kilometers per second. At that crazy high velocity, they don't even merge. They simply pass right through each other, stretching out these thin, glowing bridges of gas before escaping right back into deep space.
But, and this is key, if researchers manipulate the simulation to lower the approach speed to, say, between 100 and 200 kilometers per second, the story changes completely. At those lower speeds, gravitational capture is guaranteed. The galaxies become locked in this decaying orbit, passing through each other again and again in a massive, oscillating dance. Those cascading peaks of star formation you're seeing here, those correspond directly to each close pass, right up until the two systems finally, messily, merge into one.
Section 6. Engines of Universe Evolution.
When you zoom out over billions of years, you realize something profound. These collisions aren't random accidents at all. They are the universe's fundamental blueprint. You know, prior to the 1970s, astronomers mostly thought of galaxies as isolated island universes that just formed and evolved all on their own. But we now know for sure the universe formed through a bottom-up hierarchical process. Small pockets of stars and dark matter collided, merged, and grew. Gas compressed to form new stars, dynamical friction to force mergers, and beautifully ordered spiral galaxies were constantly randomized into these massive elliptical structures. The giant, sprawling galaxy clusters we see today are literally the result of billions of years of endless cosmic collisions.
Astronomer Halton Arp summed this up absolutely perfectly way back in 1966. He realized that these colliding, weirdly shaped galaxies are essentially massive laboratories. They are experiments furnished by nature, allowing us to test the laws of gravity, fluid dynamics, and star formation on a scale of hundreds of millions of years. Every distorted tidal tail, every stellar stream, and every starburst gives us a priceless window into the mechanics of the cosmos.
Which brings us right back to our own cosmic backyard. We started this explainer by looking at the inevitable impending collision between our Milky Way and the Andromeda Galaxy.
Knowing what we know now, that the stars will pass right through each other like ghosts, that the gas will ignite in a brilliant wave of new star birth, and that those supermassive black holes will violently awaken, we're left with a pretty staggering thought. When Andromeda finally arrives in 4.5 billion years, completely and utterly transfiguring our galaxy, what will the night sky look like to whatever life exists on Earth to see it? Thank you so much for exploring the cosmos with me today on The Explainer.